This is the 27th video in a series that I'm making to support a course in elementary number theory. And in the last video, we determined when a natural number could be written as the sum of two squares. And now we want to generalize that a little bit. So instead of a sum of two squares, we'll see when a number can be rewritten as something called a quadratic form. So let's look at a couple of definitions first, and then we'll eventually get into results. So the first definition is what a binary quadratic form is in the first place. So it's a function of the following shape. So we've got q of xy is equal to ax squared plus bxy plus cy squared, where a, b, and c are integers. And we're assuming that x and y are integers as well, although this is like a standard quadratic surface that you might see in Calculus 3 as well. Well, let's talk about some parts and characteristics of quadratic forms. So an important part of a quadratic form is something called the discriminant. And so we'll label that D, and that is b squared minus 4ac. So that's in line with the definition of the discriminant from like the quadratic formula. And I want to notice that if we define D to be this b squared minus 4ac, then we can complete the square on our quadratic form so that it looks like 1 over 4a times 2ax plus by squared minus d times y squared, where that's this discriminant. And now the sign of this discriminant will give us a lot of information. So if d is less than 0, then that means this minus d is always bigger than 0. So that means this term right here, which is always squared, and this term right here, which is always squared, will always be positive. The stuff inside those parentheses. Well, of course, unless x and y are both 0, but that's the case we're not really worried about. So that means the sign of our quadratic form is completely determined, in this case at least, by the sign of a. So if a is bigger than 0, then our quadratic form is always bigger than 0, and we say it's positive definite. And if a is less than 0, then our quadratic form is always less than 0, and we say it is negative definite. And those are mostly the cases that we're interested in. But if d is bigger than 0, then qxy is something called indefinite. And if q equals 0, then qxy is semi-definite. So now let's look at another definition, building towards an observation. So quadratic forms P and Q, maybe the Q has coefficients A, B, and C, and the P has coefficients A prime, B prime, and C prime, if you want to write them down. These are said to be equivalent if Q of xy equals P of uv, where uv and xy are related just via a change of variables. So here we'll have u is equal to px plus qy, and v is equal to rx plus sy. So notice as a vector, we have uv is equal to the matrix pqrs times the vector xy. So that's an important thing to notice. And then we're requiring p, q, r, and s to be integers and ps minus rq to be equal to 1. But that means that this matrix right here is in something called the unimodular group. In other words, capital SL2Z. So it's all 2x2 matrices with entries in Z that have determinant 1. And this indeed makes a group. If you've taken abstract algebra, you know what a group is. Okay, and so now let's make the following observation, which puts this notion of equivalence in terms of similarity of matrices. Well, so we've got q of xy, well, that's ax squared plus bxy plus cy squared, but we can rewrite that as the product of this row vector, this matrix, and this column vector. So we've got row vector xy, A, b over 2, b over 2, c, and this column vector xy. So it's pretty easy to check that if we multiply these all together, we get this scalar function right here. But then we can take this matrix PRQS, which is in fact PQRS transpose or PQRS inverse. Transpose and inverse will be the same thing in SL2Z though. and PQRS over here and factor them out of our matrix A, B over 2, B over 2, C. And that'll give us A prime, B prime over 2, and C prime. But now we'll recombine these. So this matrix here with XY, we'll label that UV, just like this is happening up here. And then we'll take this PQRS and the XY, combine them together and get this UV as a column vector. But notice that's exactly the expression for P UV if we were to multiply this out, kind of like we did up here. Okay, so let's introduce a little bit of notation. I don't know if this is standard, but this is what we'll use in the video. So for this change of basis matrix, I'll use the letter capital T. And then for the matrix associated to a quadratic form Q, I'll use A sub Q. So notice we've got something like this going on. We've got this is like A sub Q. Maybe we could write this as the vector X transpose, and then this is the vector X. And then here we have, this is A sub P because it's the matrix associated to the quadratic form P. Here we have our change of basis matrix transpose. So we've got T transpose. That's a little sloppy, but you know, that's how it goes sometimes. And then we've got X transpose here, and then we've got T here, our change of basis matrix, and then an X there. Now we can combine these together to get this matrix, or this vector U. And then here, this is our matrix AP, and there's our vector U as well. So you can see all of this is happening in the world of linear algebra pretty nicely. But then, since we know similarity of matrices, and this really is similarity of matrices because T transpose is equal to T inverse in this case, like I said, we know that similarity of matrices is an equivalence relation. So that means this notion of equivalent quadratic forms is also an equivalence relation. So we don't need to prove that on its own because it follows immediately from the similarity of matrices. Okay, so now that we've got a little bit of a setup, I think we've got one more definition to introduce before we can start proving things. Okay, we've got another definition and then our first proposition of the video. So we say that a quadratic form represents an integer n. I guess I should say my quadratic form here has name Q if there exists x naught, y naught, which are integers, such that Q evaluated at x naught, y naught equals n. Furthermore, if x naught and y naught are relatively prime, in other words, their GCD is 1, we say Q properly represents n. Now I want to notice that in the case of the simplest quadratic form, Q of xy equals x squared plus y squared, this is the sum of two squares problem, which was covered in the last video. So that should give some motivation why what we're doing here is really a nice generalization of that sum of two squares video. Okay, so our first proposition, and that is if P and Q are equivalent quadratic forms, then P properly represents n if and only if Q also properly represents n. And then the discriminant of P and Q are the same. Okay, well, let's get into the proof of part one. Actually, before we do that, let's get a little bit of setup. So if P is equivalent to Q, then there exists some T in SL2Z, as we discussed on the last board, such that AP equals T transpose AQT. But notice that we could flip this to say that this is equivalent to saying that AQ is equal to T APT transpose. Just by left multiplying by T, which is T transpose inverse, and right multiplying by T transpose with it, which is T inverse, like we had discussed before. Okay, so now we're ready to jump in to the proof of part one. So we'll only do a single direction here, and that's because the two directions are essentially the same, except we just replace the letter P with the letter Q. Okay, so let's first suppose that we have x naught, y naught, which are integers, such that p of x naught, y naught equals n. So in other words, n is represented by p. We'll get into the properly part later. But now let's take this equation involving a quadratic form and turn it into a matrix equation. So that means that x, y, and then the matrix associated with p, which we'll call AP, times x naught, y naught. So we've got row vector on one side, column vector on the other side, equals n. But now we can take this AP and replace it with T transpose AQT. So let's see, that's going to give us x naught, y naught times T transpose times AQ times T times x naught, y naught. But now we'll just push these two things that are hugging AQ together. We'll call this U naught, V naught. But this is U naught, V naught in column form. And we know that those are transposes of each other because, well, x naught, y naught is the transpose of column x naught, y naught. Okay, but that is exactly equal to Q evaluated at U naught, V naught. But on the other hand, this is also equal to N from the calculation that we did up here. So that means that Q represents N. So we started assuming P represents N and we ended with Q representing N. Now we just have to do the proper representation. So let's suppose that the GCD of x naught and y naught is equal to 1. Well, so that tells us that there exists alpha and beta, which are integers, such that alpha x naught plus beta y naught is equal to 1 by Bézou's lemma. Okay, but also we know that x naught can be rewritten as p u naught plus q v naught. And then y naught can be rewritten as r u naught plus s v naught, where that's related to our change of variables matrix here. So notice I've kind of changed the role of my x matrix and my u matrix from the last board, but these are kind of symmetric ideas, so I don't think it's a big deal. Okay, so where do we go from here? Now we'll take these two expressions for x naught and y naught and plug them up here into x naught and y naught. Then we can reshuffle a lot of things, and we'll see that we will form an equation which is something times u naught plus something times v naught equals 1. So it doesn't quite matter what those coefficients are. It's easy to calculate, though. It's just a bit of like symbolic manipulation. But if we can take u naught and v naught, take an integer linear combination of them and get 1, then that implies from stuff that we did much earlier in the course that the GCD of u naught and v naught is equal to 1. But that GCD of being 1 is exactly what we need to add properly to this representation of n by p. Okay, now let's maybe get rid of this bottom bit and we'll do the proof of part 2. So let's recall on the last board, we had this equivalence of our two quadratic forms in terms of this matrix equation. Now we want to claim that their discriminants are the same. So let's first maybe define some coefficients to build our quadratic form p of xy. So let's say that's equal to ax squared plus bxy plus cy squared. Okay. But let's notice that that makes AP, the matrix associated to this, A, B halves, and C. Now we want to look for a relation between the discriminant here. So I'll just say DISC for discriminant, which we recall is B squared minus 4AC, and this matrix here. So we're trying to assign a number to a matrix. Now the easiest way to do that is with something called the determinant. So that should be our first guess. So let's see what happens if we take a determinant of this matrix. Well, we'll get AC minus B squared over 4, just from like standard determinant rules. But notice that if we take this guy right here and multiply it by -4, we get this one up here. That's our relation between these two objects. Okay, so now I think we can get to the proof. So maybe I'll use delta for the notation for discriminant. So let's see, delta p, so the discriminant of p is equal to b squared minus 4ac, like we just talked about. But that is minus 4 times the determinant of ap. Okay, but now that's going to be equal to minus 4 times the determinant of T transpose, which recall that's T inverse, AQT. But recall that the determinant is a multiplicative function. So this gives us minus 4, the determinant of T inverse times the determinant of AQ times the determinant of T. But then the determinant of T is 1 by our definition of T being from SL2Z. But the determinant of T inverse will be the inverse of the determinant of T. So it's just 1 over 1. In other words, it's 1. So in the end, we get this as minus 4 times the determinant of our matrix AQ. But now that's going to be exactly the discriminant of our quadratic form Q by this observation that we had up here that we used in our first step. So we finished this proof of part 2. Now that we've got that taken care of, we're going to introduce another definition and prove some results related to that definition. So now for a new definition, we say that a quadratic form Q of xy, which is ax squared plus bxy plus cy squared, is reduced if one of these conditions holds. So we've got b is between negative a and positive a. That can include positive a, but not negative a. And then a is less than c. Or a is equal to c, and b is between 0 and a. So those are our possibilities. Now, before we get looking at our theorem over here, let's recall, as we've done on the last boards, that we often use a lot of linear algebra here, and we'll do that in this case as well. So a sub q, in other words, the matrix associated to this quadratic form is given by a, b halves, and c. So now let's look at our theorem. That says that every positive definite binary quadratic form, in other words, every object like this that is positive definite, recall that definition from the first chalkboard, is equivalent to a reduced form. So in other words, we can find a matrix to conjugate that thing with so that we end up with these conditions. Okay, so let's maybe jump into the proof. So we're going to consider these following 3 matrices as tools. So the first one will be U, which is 0, 1, minus 1, 0. And the second 2 come in a family. So I'll call them V plus minus, and that's equal to 1 plus minus 1, 0, 1. And furthermore, we want to introduce the following like time-saving notation. And that is if we start out with a matrix AQ and put an arrow over it with a U, that turns into U transpose AQ U. So it's not multiplying by U, it's conjugating by U. And then the same thing happens for doing this action with V. So arrow over it with a V plus minus, we get V plus minus transpose, depending on if we're doing the plus or the minus, and then AQ, and then V plus minus. So that way we just don't have to write the conjugation by these matrices over and over and over again. I think this is going to be quite time saving. Okay, so now we've set AQ equal to this object right here. And these numbers are arbitrary at the moment. And what we want to do is apply these 2 operations, which notice leave you with an equivalent quadratic form until one of these is satisfied. So let's start with the following observation. That is, if we take A, B over 2, B over 2, C, and we apply U, in other words, we conjugate by U, we'll get the following new matrix. So I'm not going to do the linear algebra here. That should be like fairly straightforward. So we'll get C minus B over 2 minus B over 2A. So this thing has the effect of swapping A and C and then negating the things on the off diagonal. So that's really good to keep in mind because by these rules up here, we always want C to be bigger than or equal to A. And by C, I just really mean the portion of the matrix right here. So if we've done a lot of operations maybe involving V, and we end up with this guy right here being bigger than this guy right here, then we can just apply U and then we're in the right order again. So now let's also notice the action of V plus minus. So we'll have A, B halves, C applied on by V plus minus will give us A and then plus minus A plus B over 2 plus minus A plus B over 2. So that's going to be the off diagonal terms. And then A plus minus B plus C. And that's actually quite helpful because that will allow us to move these things on the off diagonal until B is in the correct range. Okay, now that we've made those observations, we're ready to dive into the meat of this proof. Okay, I've recalled the action of our matrices U and V at the top, and now we're ready to jump into the proof. So I guess maybe there's a case one of this, which is maybe B is already in the correct range. So in other words, B is on the interval minus A to A, where we don't include the bottom of this interval, but we do include the top of this interval. In other words, B is all set. Now this breaks down into three cases. If A is less than C, then we're good, because this thing is satisfied right here. And then part two, if A is equal to C, then we're not good. So if A equals C, we might be good. If B is positive, then we're good to go by this rule over here. But if B is negative, so let's write that down. If B is less than 0, what we'll do is apply V plus once. And that'll take something from the negative part of this interval to the positive part of this interval. And now finally, if we have A is bigger than C, then we'll just apply U. Remember, all that does is switch the diagonals here. It negates the off diagonals, but if B is on this interval, then minus B will also be on this interval. So that's okay. Okay, now let's look at the second case, which is, I'll call it case 2, and that is B is outside of this interval. So I'll just like do a mock-up of a picture, and this is going to be a little bit hand-wavy, but I think it's like kind of okay. So I'm going to draw a real number line here, even though we're only really worried about the integers. So I'll put negative A right here, and then I'll put positive A right here. So notice I'll put a closed circle here, and I'll put an open circle here because that's kind of what we're interested in. Now, if B is outside of the interval, it could be way down here or it could be way up here. Just for the sake of our example, I'll put it way up here. So let's say our original value of B is here. Okay, well, what happens if we apply V minus? So that's going to replace B over 2 with this thing right here. But this replacement of B over 2 with this is equivalent to the replacement of B with B minus 2A, just because you've got to double things to make that make sense. Why is it minus? Well, that's because we're applying V minus, so we get the minus sign on the A. So let's see, we need a length of 2A. So notice that this guy right here is a length of 2A. So if we apply that to B, that will hop this thing to here. So that's going to be our next value of B, which I'll call it B1. So just to reiterate, this is an application of V minus. Now we're just going to keep doing that. So let's do another application of v minus. That'll give us a b2 here. And then another application of v minus. That'll give us a b3 here. And as you see, for this setup, we'll need one more application of v minus, and that'll give us a b4, which is on the right range. But now we've got b in the right order, and you can go back to case 1 and fix the a and c as needed. Okay, so let's run through an example. All right, now we're ready to look at an example. So we want to find the reduced form equivalent to the following quadratic form. So 133x squared plus 108xy plus 22y squared. So let's notice that our a component is most definitely bigger than our c component. So that's not satisfied in any of these cases. So that means we've got some fixing to do. So let's define this matrix A, which is 133, 54, 54, 22. Notice that's 108 over 2. Again, we see that this component is larger than this component. So the first thing that we can do is apply U to switch those, because we always want the C component to be larger. So that'll give us 22 minus 54 minus 54, 133. And now our A and C component are in the right order, but our B component is in the incorrect range. So notice our B component now is minus 108, but that is smaller than negative 22 as allowed here. So since it's smaller than negative 22, we should apply the V plus operator. Recall, that's just conjugating by the V plus matrix, if you're keeping track of it like that. Okay, so applying the V plus operator will give us the following. So we'll have 22 here, minus 32, minus 32, and then finally a 47 down here. So let's notice that our A and C are still in the right order, but our B is still smaller than negative A. Notice our B in this case is negative 64. That is too small. So that means we need to apply the V plus operator again. So let's see what that'll leave us with. That'll leave us with 22, negative 10, and then down here we'll have the number 5. Okay, well now our A and B are out of order, so we need to fix those. And we can fix those by applying a U. So let's see, that's gonna give us a 5 up here, a 10 here because it changes the sign, a 10 here, and then a 22 here. So now my A component is less than my C component. And then notice this means that B is equal to 20, but that's too big, right? Because the biggest it can be is 5 by this inequality right here. So that means we need to apply a V minus to make our B component smaller. So applying one V minus will give us 5, 5, 5, 7. And then applying another V minus will give us 5, 0, 0, 2. So that's diagonal, which is nice. But now if we've got B values of 0, we're definitely satisfied over here. So that's good. But our A and C are out of order. So we'll apply a U and we'll get 2, 0, 0, 5. And now everything is sorted out. This rule over here is satisfied. So that means that we have a reduced form, and our new quadratic form is the following: 2x squared plus 5y squared. And you can imagine it's probably easier to work with this quadratic form than it is this quadratic form. But by the equivalence, as we'll see, anything you can prove about a quadratic form like this, you can also prove about a quadratic form like this. Okay, we've got a big theorem before we finish it off. Now we've got our big theorem for today, which is in some ways parallel to which natural numbers can be written as the sum of two perfect squares. Okay, so we'll let d be negative and n be positive. They are both integers. Then n is properly represented by a quadratic form of discriminant d if and only if x squared congruent to d mod 4n has a solution. So that's good. We've studied quadratic residues and when congruences like this have solutions. So that takes this seemingly hard question and writes it in terms of something which is a little bit more familiar. Okay, let's get to the proof. This is an if and only if statement, so we've got two directions to prove. Let's prove this reverse direction first. So let's suppose that B satisfies our congruence, which we've assumed to have a solution. So that means we know that B squared is congruent to D modulo 4n. Now we'll take this fact and build a quadratic form with discriminant D that represents n. Okay, well, let's get to it. So by the definition of congruence, this means that 4n divides b squared minus d. But then by the definition of divisibility, that means there's an integer such that 4n times that integer equals this stuff over here. Well, let's just call that integer c. So we'll just name the integer c so that b squared minus d equals 4nc. In other words, that's like building off the definition of divisibility there. Okay. So now let's move some things around here. We'll solve for d. So let's note that d is equal to b squared minus 4nc. Well, that's exactly the discriminant of the following quadratic form, which is pretty easy to write down. It is nx squared plus bxy plus c. Discriminant of that guy right there. So let's go ahead and give that a name. So that's equal to, we'll call it qxy. And then another thing that we want to note is that q evaluated at 1, 0 is equal to n. So that's exactly what we need for q to represent n. So that finishes the proof of this reverse direction. Now we'll dive into the proof of the forward direction. So we're ready to look at the forward direction. So we're going to suppose that n is properly represented by our quadratic form of discriminant d. Okay, well, so what does that mean? That means there exists some numbers which I will call p and q, which are integers. They are relatively prime, so the GCD of p, q is 1, with q evaluated at pq equals n, and the discriminant of q, which I'll label by delta q, is equal to d. So that's just the hypothesis of this. But now we're ready to take that hypothesis and build towards our conclusion. So we've got these two things have GCD 1. Well, that really motivates us to find two integers, which I'll call r and s, such that pr plus minus qs is equal to 1. So we can always do that by Bézou's lemma. I mean, this is 27 videos into a number theory course, so this should be like secondhand at this point, hopefully. Okay, great. And so now we see that q is similar to something that I'll call q prime with q prime of xy equal a prime x squared plus b prime xy plus c prime y squared, and a q prime, in other words, the matrix associated with this quadratic form, is equal to t transpose a q t, where AQ is the matrix corresponding to this original quadratic form, where we are carrying the notation T equals PQRS, like that. Okay, so that was kind of a lot, but it sets up a really nice observation. So now let's notice that A prime is equal to Q prime evaluated at 1, 0 by our construction here. But that's exactly equal to Q evaluated at PR. So we can see that by our construction with this PQ minus RS equals 1, this matrix T, and stuff like that. But now Q evaluated at PQ is equal to n from our original assumption. But now we've constructed a new quadratic form, which is a little bit nicer in the way that it represents n. It represents it with 1, 0 instead of pq. But now let's go ahead and calculate the discriminant of this. So I'll just put DISC to say that we're calculating the discriminant. So on the one hand, it's the same thing as the discriminant of Q, which is equal to D. But on the other hand, it's equal to B prime squared minus 4A prime C prime. But from this formula right here, A prime is equal to N. So we have B prime squared minus 4N times C prime. But now let's look at the extreme left and right-hand side of this equation. And notice that that tells us that B prime squared is congruent to D modulo 4n, which is exactly what we wanted to end up with. Okay, now that we've proven this big theorem, let's see an example. Now we're going to see the power of that previous theorem. And so we're going to show that there is a solution to the quadratic congruence x squared plus 5y squared equals p, where p is prime, if and only if p is congruent to 1 or 9 mod 20. Okay, so let's look at the proof. So by the previous theorem, the one that we just got done proving, this is equivalent to the congruence x squared congruent to negative 20 mod 4p having a solution. But now notice x squared congruent to negative 20 mod 4p has a solution if and only if x squared congruent to negative 5 mod p has a solution. But now notice that's if and only if the Legendre symbol minus 5 by p equals 1. Remember, the Legendre symbol is like a yes or no question. If the output is 1, then this type of thing has a solution. If the output is negative 1, then this type of thing does not have a solution. But now let's notice that there's another condition here. And that other condition is that p is a perfect square modulo 5. That's because if we reduce this thing mod 5, we get p equals x squared. So we can encode that in a Legendre symbol as p by 5 equals 1. But then by quadratic reciprocity, since 5 is congruent to 1 mod 4, we can actually flip that around to 5 by p equals 1. But now from a homework problem in class, we know exactly the primes that satisfy these two Legendre symbol equations. So minus 5 by p is equal to 1 if and only if we have p is congruent to 1, 3, 7, 9 mod 20. And then 5 by p is 1 if and only if p is congruent to 1 or 4 modulo 5. So again, that's from an exercise in the class that I'm teaching. If you haven't done something like this before, I would implore you to work out some of these examples. They're really helpful for coming to grips with the practice of doing these kind of things. But now we want to slam these two together. That's a little bit tricky while this is mod 20 and this is mod 5. So we want to extend this mod 5 to a mod 20. So we can do that and we'll see that p is congruent to 1, 4, 6, 16, or 19 mod 20. So obviously there's a lot of values there. But recall that our prime has to satisfy both of these congruences. But that means that it's either 1 or 9 because those are both of the ones that are in each of these lists. So that tells us that we have p is congruent to 1 or 9 mod 20. So that finishes off the proof of this proposition. And that's a good place to stop.